Hello, this is Dr. Park's practice test 2 for the second midterm in MA 265. Just note that at the time of this recording, he has not released answers yet for these questions. I am about 90% sure that my answers are correct, but just take that with a grain of salt. I may have to, like on exam 1, re-upload something or at least clarify to fix a question that I got wrong. Yeah, here are my answers. So let's go. Problem 1, let A be a non-singular matrix with its inverse given here. So we know right off the bat that A is invertible, which is going to come in handy here. Which of the following statements is false? A is not diagonalizable. Okay, well, let's see if A is diagonalizable. Let's find the inverse of the inverse here, and we'll be able to figure out diagonalizability. Remember, this will come up multiple times in this exam. Diagonalizability does not necessarily imply invertibility, and invertibility likewise does not imply diagonalizability. So finding the inverse of this guy, we are going to flip the A and D entries. So A is equal to 3, 1, -2, -2. And we're going to divide by the determinant of A inverse, which is 3 minus 4, so -1. 1 over -1. So there is A right there. And just right off the bat, we know that this here is diagonalizable because it is a symmetric matrix. A symmetric matrix. All symmetric matrices are diagonalizable. And so A is not diagonalizable. That is false. A is diagonalizable. And here we go. Looking at E, we know that A is a symmetric matrix. We know that this is true since A does have an inverse. Looking at option C, we also know that this is true because A has an inverse, so we can do A inverse multiplied on the left on both sides is equal to A inverse A C. Both of these will become the identity matrix. The identity matrix times any matrix of the same dimension is just that matrix. So B is equal to C. That guy's true. And A of T is invertible. Well, we know that the only way that a matrix can be non-invertible is if its determinant is 0. We know that the determinant of A is non-zero. We know that the determinant of A transpose is equal to the determinant of A. Therefore, transposing A does nothing to its invertibility. So answer 1 is A. Problem 2, we're given A here, and we're told to find the trace of the matrix, which is the sum of the main diagonal terms of A inverse. So to get started here, we're going to need to find the determinant of A to find A inverse. I'm just going to do it the lazy way. We're going to do the cofactor expansion. So this top row, I know we could use this middle column and do one fewer step, but I'm going to do it this way. We're going to do 2 multiplied by the submatrix here formed by, the determinant of that submatrix formed by canceling out the row and column that 2 is in, multiplied by -0, okay, gotta be careful there, times the submatrix formed by crossing out the row and column, and then we'll do the same thing with +2 here, multiplied by the determinant of that submatrix. And remember, the scheme for this is plus minus plus minus plus minus plus minus plus, like that. Okay, so we will have 2 times the determinant of 0, 1, 2, -3. We can neglect that 0 term, plus 2 times the determinant of 1, 1, -3, 0. This determinant right here is 2. This determinant right here is 1 multiplied by 2 is 2. And our determinant right here is -2. So this is -2 times 2 is -4 plus 2 is -2. And that is the determinant the determinant of A. And we are almost done. We're going to have to find three cofactors, which are going to be the corresponding submatrices for crossing out the first column in the first row. To find the cofactor for this position, we're going to cross out the second column and second row to find the cofactor formed from these four guys for this position. That's our B22 term. And then finally, the cofactor formed by crossing out the third row and column, like so. And that's going to give us our first cofactor. Sorry, I should be clear. What we're really computing here is 1 over the determinant, which is -2, and we're solving for the trace. 1 over -2 multiplied by the cofactor of the 1, 1 position, which is going to be plus the determinant of 0, -3, 1, 2. Looking to our scheme over here, we're going to use another plus this cofactor, which is 2, -3, -3, 2. And then finally, another plus for this cofactor right here, which uses this matrix, and that matrix is 2, 1, 0, 0, and we are ready to compute. Both of these matrices determinants are going to be 0, and we are left with this guy right here. This determinant is -2. -2 over 2 is 1. Our trace is 1. This is, a little bit of a pain, this whole problem, to go through the whole process. But when you're doing it on your own and you know the steps to go through, a lot of the explanation is pretty redundant. Question 3, assume that the matrix A given here is invertible. What is the 2, 1 entry of the inverse of A? Right off the bat, we need to find our determinant. So our determinant of A is going to be 1 times the cofactor at that position, which is 1, 1, A, 2, minus 2 times 2, the determinant of the matrix 2, 2, 2, 1, plus 3 times 2A, 2A, 2, 1, like so. And solving this, we will get 1 minus 2A minus 4 plus 8 plus 6A minus 6. And simplifying, we have plus 4 here, minus 6 is -2, plus 1 is -1, and then 6A minus 2A is 4A. So here we have our determinant of A, and I'm going to get rid of all this stuff for a little bit more space. So if this is the determinant of A, all of our entries in A are going to be divided by this guy right here, and we know as a result we're able to cross off any answer choices that don't divide by 4A minus 1. Okay, so moving on, we're looking for the 2, 1 entry of the inverse of A. If you find inverses the way I find inverses, one of the steps of finding that inverse is reflecting everything along the main diagonal, which just realized I should have really said transposing, which is the same thing. And so since that ends up happening after we find the cofactors for all the positions, we know that instead of finding the cofactor for this position, which will give you -2 plus 3A, which will lead you to answer choice D, you want to find the cofactor for the transpose of that position, the 1, 2 entry instead of the 2, 1 entry. So finding this cofactor, we are going to get 2 minus 4, and since we know that our plus minus plus scheme still holds, this position here will have a negative term, and so let's see, A inverse at the 2, 1 position is going to be +2, because remember we found -2 from this little submatrix here as that determinant multiplied by that sign. And so our answer is C. Okay, problem 4. Given constants a and b, consider the linear system. Given here 9x plus 2y equals a, and 4x plus y equals b. Find a solution of the linear system by using Cramer's rule. So Cramer's rule says that if we first go and express this system in terms of matrices, we have 9, 4, 2, 1 multiplied by xy is equal to ab. And what Cramer's rule says is that we can solve for x by setting up the equation which has the determinant of this matrix here, but replacing the x column, so this 9, 4, replacing that with a and b, and then leaving our other column alone, over the determinant of the matrix here with nothing done to it. So that's 9, 4, 2, 1 just by itself. And then y, similarly, is going to be 9, 4, ab, the determinant of that, all over 9, 4, 2, 1. And it's pretty nice in this situation that the determinant of 9, 4, 2, 1, our matrix in the denominator, is just 1. So we can get rid of both of these guys. And then solving this determinant is pretty easy. X is equal to a minus 2b, and y is equal to 9b minus 4a. And we're done. And I'm going to move this up a little bit to get out of the way for our next question. Question 5, given that the determinant of this big guy right here is equal to 4, what's the determinant of this even bigger thing down here? So first off, let's identify what they have done to this matrix. I'll call this matrix A. What have they done to A to get to this new determinant that we're trying to take? Well, they've added 3 row 4s to row 3. Well, we know that adding row 4, adding any rows, any factor of any row to another row will do nothing to the determinant. So we can cross off all of these without changing the determinant of this guy. Okay, next we see that they've multiplied a row by a factor of 2. And we know that when we multiply a row by a factor of 2, it will multiply the determinant by a factor of 2. And in fact, that holds for columns. That holds for columns as well. And then finally, we see, I'll cross off these 2's because we've dealt with them. We see that they have switched row 1 and row 4. And they've switched column 1 and column 4. And if we switch those back, we will have to multiply our determinant by -1. And so overall, once we do, these 3 things, get rid of the +3 row 3, get rid of the multiplying row 3 by 2, and then flip these 2 rows back, we will have this guy right here. And if we want to get back from our first determinant to this guy, we will have to do these transformations here. We'll have to multiply our determinant by 2 and flip 2 rows, which will invert it. So this gives us a determinant of -8. Question 6, if A is a 3 by 3 matrix with a determinant of 5 and B is equal to 2A, then what is the determinant of A transpose times B inverse? So right off the bat, let's split this up a little bit. The determinant of 2 matrices multiplied together is the same as the determinant of A transpose, not A squared, multiplied by the determinant of B inverse. And this just helps us separate what we're thinking about a little bit. We know that the determinant of A is the same as the determinant of A transpose, so the determinant of A transpose is also equal to 5. So we can replace this bit with a 5. And we know that since A is a 3 by 3 matrix, multiplying 2 into A will multiply every row by a factor of 2. And so the determinant of 2A, so determinant of 2A is going to be the determinant of A multiplied by 2 raised to the dimension of the matrix, which is 3. Because we're doing it once for every row or every column that the matrix has. So this will be 8 times the determinant of A, which is 40. We also know that the determinant of 1 over A, oh, sorry, that's not what I meant. The determinant of A inverse is the same thing as 1 over the determinant of A. And since the determinant of B must be 40, like we found over here, because B is equal to 2A, then the determinant of B inverse is 1 over the determinant of B. So that will be 1 over 40. And 5 over 40 is 1/8. And we're done. Problem 7, this is one that a lot of people had some questions about, and so did I. I had to get answer choice C explained to me, but now, I'm pretty sure everything is clicked. We'll see about that. Let P3 be the vector space of all polynomials of degree less than or equal to 3. Which of the following sets, it could be one, could be multiple, is or are subspaces of P3? Let's put our little rules out to the right. The rules that if we abide by all 3 of these will be considered a subspace. So we must have to have the 0 vector. I'll draw that a little bit differently. We have to include the 0 vector. We have to be closed under vector addition, and we have to be closed under scalar multiplication. We'll start to get into what all 3 of these guys really imply as we go through these options. So option 1, 1 plus t squared. Is that a subspace of P3? Well, let's start with our first rule. Does it include the 0 vector? Well, is there any number that you can plug into t which will solve 1 plus t squared equals 0? And in fact, there is not. The roots of this are plus or minus I, and we're looking for real valued solutions for this. And as a result, A is not a subspace of P3. Option B, we're looking at AT plus BT squared plus quantity A plus B t cubed, where A and B are real numbers. Well, if A and B are both equal to 0, which is part of this set here, because we're looking at all real valued A's and B's, it's clear that we do include the 0 vector in this set. So that first rule is A-OK. So let's choose an arbitrary A1, A2, B1, and B2 that are in this set, and let's check for closure under vector addition. So our first vector will be A1t plus B1t squared plus A1 plus B1 t cubed, and we are adding to that A2t plus B2t squared plus quantity A2 plus B2 t cubed. And we're going to see if this is of the same form as the original vectors that we started off with. And so adding these, we're going to get A1 plus A2 A1 plus A2t plus B1 plus B2 t squared plus A1 plus A2 plus B1 plus B2 t cubed. And looking at this closely, we see that A1 plus A2, well, we could just express that as another value A3. This can be a B3, and over here, A3 and B3. And we see that if we form another vector out of this, A3t plus B3t squared plus A3 plus B3t cubed, this is exactly like, you know, I'll be a little bit more clear. This is exactly like the ones that we started off with, our example vectors or polynomials that we added together to begin with. So it's clear that when we take two arbitrary elements from this set and add them together, that we get another member of the set. So we are closed under vector addition. And finally, scalar multiplication is a little bit of the same. Let's choose some C, which is a real number, and multiply our polynomial AT plus BT squared plus A plus B T cubed. Let's multiply all of that by C. C, 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 C. And the nice thing here is that we are close under scalar multiplication because CA is just another real number, CB is just another real number, and so we can express CA as, you know, just another A, and CB as just another B, and we will get another element of the set. So option B obeys all the rules, so it is a subspace of P3. Now let's take a look at C. If A and B are 0, then the polynomial is equal to 0, and so we clearly do include the 0 vector. And I'm just going to show a little bit of a different way to write these out, which I actually like a little bit more of, and I like it a little bit more, and I should have used it last time for B. It would have made things a little bit easier. We can treat t to the 0, which is really what that term is, t to the 1, t to the 2, and t to the 3 as positions in a vector like this. So we can treat this polynomial as a whole as a, b, 0, because you know, it's a t0, b t1, t2, t3, and this is just another way of expressing this polynomial here. So let's choose arbitrary a1s and b1s and a2s and b2s and try to add these guys up. So we're going to take our first vector and add a2, b2, a2, b2, and 0. And we are going to get a1 plus b1, b1 plus b2, and up here I actually meant a2, not sure what happened there, a1, b1 plus a2, b2, 0. And right away, we have a problem here because these first two elements are perfectly fine. We can take a1 plus a2 and just express it as, you know, some other a3. Let's define these right here. A1 plus a2 is equal to a3, and b1 plus b2 is equal to b3. So this here will simplify down to a3, so that component is closed under vector addition, and this one will simplify down to b3. That one's good, but a1 b1 plus a2 b2 is no good. We cannot express that in terms of a3 and b3. So in the end, we are not closed under vector addition. We fail our second rule up there, and so C is not C is no good. Okay, what about D? we have some arbitrary polynomial that's a member of P3 where P2 is equal to 0. Well, let's take A as an example. That's a polynomial that's a member of P2. Just to show you, what could be happening behind the scenes here. Although, P2 for option A is not equal to 0. But let's try to find some polynomial that is. Well, t minus 2 is a polynomial that's a member of P3, and it at t is equal to 2 is equal to 0. And there are a bunch of these, but the important thing to recognize is that all these polynomials, let's see if I can figure another one out. Whatever this thing expanded is, t minus 2, t plus 1, or you could have t minus 2, t plus 10, t minus 1. Anything like that, and you can expand those out and really test it for yourself. But anything in P3 that has a solution that has the 0 vector in it, and I'll just be clear, we've already succeeded on that goal, can be expressed as a span. So this first guy here can be expressed as the span of -2, 1, 0, 0, where we're taking all those components out. This guy right here, I'll just to show off, not show off. It's not showing off by expanding this thing, but t squared minus t minus 2, we could express this as -2, -1, 1, 0. And all of these spans are subspaces because we know that anything that we can call a span is a subspace. Right? These all would be lines passing through 0, 0 in 4-dimensional space in a way. That's just another weird way of thinking about it. Hopefully this was a helpful explanation. I'm actually really unhappy with how this question went as a whole, but I don't know. Maybe that was okay. So both B and D work. D because we can express any polynomial that passes through 0 as a span, and therefore it is a subspace, and B because it passes all of our tests, whereas A fails the 0 vector test and C fails vector addition. Question 8, let's find the basis of the null space of A. Let's write this out. 1, 2, 2, 2, 2, 3, 2, 3, 1, 3, 3, 1, 2, 2, 2. Okay, I'm going to subtract 3 row 1s from row 2. We'll get 0, -4, -3. We'll get -3 in that position, and -5 over here. I'm going to subtract 3 row 1s from row 3. 0, -5, -4, -4, -4. I will invert all 3 of these, not all 3, all 2 of those rows, like so. And let's see what else we can do. Let's subtract. No, let's actually not do that. Let's subtract row 2 from row 3. We will get 1, 1, -1, 1. Let's subtract 2 row 3s from row 1. That will give us 0, 0, 4, 0. Let's subtract 4 row 3s from row 2. We'll get 0, -1, 9, -1. And just to make things a little more clear, we're going to switch row 2 and row 3. And let's see, invert row 3 and subtract it from row 2. That will give us 0, 8. I always forget what these used to be. One sec. Yep. 0, 8, and 0. Okay. Sorry you had to sit through that. But now we are ready to find the basis of our null space. We know that the null space is going to be the solution of ax equals 0. So we're solving this right here. We see that one of these solution vectors for our free variable x4 is going to be -4, -8, 9, 1, 0, because, just to reiterate, x1 here is equal to -4 x4 if we move that over to the other side of the equation. X2 is equal to -8 x4. We get 9 here, and of course x4 is equal to 1 of itself. So there's our first vector, and then our second vector is our solution set for x5. That's going to be 0, 0, -1, 0, 1, and that is option A there. And just to be super duper clear, x1 and x2 are not dependent on x5. x3 is equal to -1 x5, and x5 is equal to 1 of itself. Question 9, let's compute the following determinant here. So we're going to use a little bit of a different determinant method, but we have to remember even now our plus minus plus thing, plus minus plus minus minus plus minus plus minus plus minus plus plus minus minus plus. Okay, I hope I did all of those correctly. We are going to notice that we can take this determinant by multiplying 2 by the matrix that we get by crossing out the row and the column that 2 is in. And this is very convenient because we have these 3 zeros. But we have to note what sign 2 has over here, which happens to be a positive sign. So we're looking good, and that is going to be 2 multiplied by 0, 3, -4, -5, 0, 3, 0, 5, -7, the determinant of this whole thing. And now, just to get even more complicated, we notice that since we have a 5 alone in this row with 2 other zeros, we can, take that out, noting the sign that position would have, which is, that's not a negative, there we go, which that position in this matrix has a negative sign, so we can take 2 times -5 out and multiply it by the matrix that's left, which is 3, -4, 5, -7. Out here, we're just going to get 10, and -21 plus 20 is -21 plus 20 is -1, so our answer for problem 9 is B, -10. Question 10. Suppose that A equals P D P inverse, where P is a 3 by 3 invertible matrix, and D is the diagonalized form of A. And this is important because we know that this diagonal matrix will encode the eigenvalues of A. We are told that A is equal to 2i plus 3a plus a squared, which of the following is true. So essentially, we are trying to figure out, 1, if B is always diagonalizable, and if B is always diagonalizable, what its eigenvectors, sorry, I keep messing that up, what its eigenvalues are. So we're going to need a couple facts here. Well, first off, we know that A is diagonalizable because it has 3 distinct eigenvalues. That means it will always be diagonalizable as a result. And here are 3 things that you can look up proofs for. I did, and you're just going to have to roll with me on them. If A has eigenvalues has an eigenvalue lambda 1, a squared is going to have the eigenvalue lambda 1 squared. And 3a will have the eigenvalue, or sorry, I'll be more general, c, some scalar c multiplied by a, that matrix will have the eigenvalue c lambda 1. And then finally, a plus c times the identity matrix will have the eigenvalues, we'll have an eigenvalue, lambda 1 plus c. And so using these three facts, we can see what the eigenvalues of b, are going to be. We see that a squared will have eigenvalues 1, 4, and not negative 9, 9. 3a will have eigenvalues 3, 6, negative 9, and all of these guys, a squared plus 3a, collectively we can just add these eigenvalues together, and that's another thing that I should note. If a has lambda 1 as an eigenvalue and b, this is a different b, has lambda 2 as an eigenvalue, a plus b will have lambda 1 plus 2, lambda 2 as an eigenvalue. So using this fact, we can add these two guys together and see that collectively these two will have eigenvalues 4, 10, 0. And then if we add on a 2i, that will just, remember using this rule here, we'll add whatever constant is multiplied by I to all of our eigenvalues. So we have 6, 12, and 2. And so, drum roll please, because this was a real pain to figure out this entire question. I can really dislike this question. But it's kind of pretty in the end, because just by finding these three, we know that both B is diagonalizable because it has three distinct eigenvalues, and also we know what those eigenvalues are, and we know that the diagonal matrix that it forms will be composed of those eigenvalues. So B is our correct answer. Problem 11, which of the following statements are true? If lambda is an eigenvalue for A, then negative lambda is an eigenvalue for negative A. I'm going to choose a very simple example for this, but if you want more proof, like more mathematical rigor, I am certainly not the person to go to. Let's find the eigenvalues for this matrix here, just the 2D identity matrix. We're going to solve this guy right here, the determinant of A minus lambda I. This will give us lambda squared, or I don't even need to expand it out. This will give us 1 minus lambda and 1 minus lambda. And then we see pretty quickly that if we negate our identity matrix, we are going to end up with opposite eigenvalues. So this, in all cases, actually, is true. 2, if 0 is an eigenvalue for A, then A is not invertible. Well, having 0 as an eigenvalue for A, we can think about that in the context of an upper triangular matrix, just to have it make a little bit more sense. Let's see, we could have, let's just stick in 2D. If we have 1, 0, 0, 1, since this is an upper triangular matrix, our eigenvalues are just going to be the entries of our main diagonal there. And so since A, what am I talking about? A, since 0 is an eigenvalue here, we see that also our matrix is not invertible. Also, you can think about an eigenvalue graphically as, the amount that values on an eigenvector get scaled by when you apply the transformation. And an eigenvalue of 0 implies that there's a whole line of vectors that are all getting scaled by 0, essentially smushed into the origin, which you can think of as adding a dimension to the null space, where there's been this whole set of vectors that have been added to the dimension of the null space, or the solutions of AX equals 0, the solutions of, when you apply this transformation, what ends up on the origin. And so this is true. Option 3, if an m by n matrix A is diagonalizable, then A has n distinct eigenvalues. This is just a definition. This is something that you should be very aware of. Okay, option 4, let A equal 2, 0, 1, 2. Is it invertible and diagonalizable? Well, it's obviously invertible because its determinant is 4, but is it diagonalizable? So if it's diagonalizable, we want it to have n distinct eigenvalues. And let's solve, or sorry, we want to have n eigenvectors. There we go. So let's solve for that. We're going to solve 2 minus lambda, 0, 2 minus lambda, and 1. And in fact, I'm not even going to solve this because we know that the solution of this is going to be lambda equals 2 with a multiplicity of 2. And that's all well and good. So now solving for our eigenvectors, we're going to plug in lambda equals 2 into A minus lambda I. So that's going to give us 0, 0, 0, 1. And when we solve this, this augmented matrix here to give us our eigenvector, we're going to see that this solution is 1, 0. And since we only have one eigenvector, we would need 2 to be diagonalizable. And a nice way to think about this, actually, this is just an afterthought. So 4 is incorrect. 1, 2, 3 is our correct answer choices. 11 is C. There we go. Another cool way to think about it is that a matrix is only diagonalizable if its eigenvectors span n-dimensional space. So in this case, because we only have one eigenvector, it does not span R2. It cannot span R2. Okay. Problem 13. Define a transformation from R2 to R2 by T of x equals AX, where A is given there. Which of the following is a basis for R2 with the property that the beta matrix for T is a diagonal matrix? So really this is just a roundabout way of saying solve for the eigenvectors of A. And if you had asked me about an hour ago why we needed to solve for the eigenvectors of A, I would have a very good answer for you. But at this point, I do not at all, and I kind of just want to be out of here. So we're going to solve for the eigenvectors of A. So we're solving 2 minus lambda, 3 minus lambda. Well, the determinant of this, so I'm just going to skip the step and multiply them in. 2 minus lambda multiplied by 3 minus lambda, which is just lambda squared minus 5 lambda plus 6. That's a 5, but we're subtracting a 6 anyway. So it's out of there. This equal to 0. This factors, and we will see that our solutions are lambda equals 0 and lambda equals 5. When lambda equals 0, this matrix is 2, 3, negative 1, negative 6. Nothing has changed. And we can simplify this down to 1, negative 3 up there. And so the eigenvector that comes out of this is going to be 3, 1. And taking lambda equals 5, negative 3, negative 2, negative 1, negative 6 is the matrix that comes out. And we can simplify this down to 1, 1, 2, 0, 0. And that will give us an eigenvector of negative 2, 1. And so our answer, sadly, is A. And I say sadly because I'm really going downhill fast. This has taken me a lot longer to go through than I expected. And yeah, you all know the feeling when you're an hour and a half into an exam and you just want it to be over. So I'm pretty sure that A is the correct answer, but I'm really, really unhappy with that explanation there. 13. Yeah, I know it's A. Okay. 14. Let A be an n by n matrix. Which of the following is or are not equivalent to the fact that A is invertible? If the columns of A are linearly independent, A is invertible. That's a fact. Diagonalization, if you remember what I said at the very beginning of the video, diagonalizability does not imply invertibility and vice versa. So 2 is incorrect. Well, I should be marking these differently. This is not equivalent to the fact that A is invertible. This is equivalent to the fact that A is invertible. 3, the dimension of the null space of A is 0. That is equivalent to the fact that A is invertible. You can kind of conceptualize it visually by thinking of the null space as, you know, all of the space that gets squished onto the origin after you apply the transformation. And we know that invertible matrices are ones that stay within the dimension of space that they started in. So, you know, we can't take R2 and squish it onto a line or a point and still have an invertible matrix. And the determinant of A being equal to 0, that is equivalent to a matrix being non-invertible. So 2 and 4 are our answers. And I just chose 3 and 4. I meant option D. Problem 15. Which of the following matrices are diagonalizable? Okay, this is much easier than it seems. 4 is diagonalizable because it's a symmetric matrix. If you take the transpose of this, you'll get exactly the same thing, and that's the dimension. That's the definition of is symmetricity a word? I don't know, of matrix being symmetric, and as a result, 4 is symmetric. We're good on that. 3 is also symmetric because it is an upper triangular matrix with 3 distinct eigenvalues down the main diagonal. If both of those facts are true, then our matrix is diagonalizable. Taking a look at 2, let's try to solve that. We are going to get 1 minus lambda times 1 minus lambda is equal to 0. This will expand to 1 minus, I don't need to expand this. Our solutions are -1 with a multiplicity of 2. Let's see what that solution gives us. If we apply lambda equals -1, we are going to get 2, 0, -2, 2, and we can solve this and see that we do not have a solution, or at least the solutions that we get are not two-dimensional. We would need 2 free variables here because we only have 1 eigenvalue to make our eigenspace two-dimensional. And so, and by having a two-dimensional eigenspace, we will have n linearly independent eigenvectors, which would make this diagonalizable, but we don't, so this is no good. And finally, number 1, let's solve this. We are going to solve 1 minus lambda times -2 minus lambda minus 4 is equal to 0. That's a bad lambda. And we will get -2 plus 2 minus 1 plus lambda squared minus 4. So this is a -6. And solving this, we'll get lambda plus 3, lambda minus 2. We have two distinct eigenvalues. We can plug these in and see if we get two distinct eigenvectors. I have a feeling that we will. If we plug in lambda equals 3, we will get -2, -5. No, that's wrong. -2. Oh, sorry. I'm really losing it right now. Lambda is equal to -3 and 2. If we plug in lambda equals -3, we will get 4, 4, 1, 1. And this will give us an eigenvector. Let's see, we can simplify this down to 1, 1, 1, 0, 0. So -1, 1. There's one eigenvector. And then if we plug in lambda equals 2, we will get -1, 1, 2, -2. This will simplify down to an eigenvector of 2, 1. Okay, so 1 is diagonalizable. 1, 3, and 4 are diagonalizable. D is our correct answer for problem 15. Okay, I very well might re-record this and re-upload it because overall I'm extremely unhappy with how this went overall. I'm sure it'll seem a lot better to you when I cut out all of the bad runs, but this was an interesting experience. I hope some of this was helpful. Oh my God. See ya.